Yeah, it's not exactly circle packings, but it's close, and it's got links to it. But yeah, I'm going to be talking about, instead of packing circles, we're going to be packing kind of the next level of generalization, which is going to be the centrally symmetric convex bodies. So we've just got a list of terms here. Convex body is just going to be a compact convex set, but we assume it's not flat, it has some interior. And centrally symmetric just means if one point's in the shape, then its negative is also in the shape. Okay, so it will have 180-degree symmetry. Okay, and then a homothetic packing is quite a long word, but all it means is that when we're packing our shapes, what we're doing is we're taking our original, for the most part, it's going to be a centrally symmetric convex body, but it can also just be a convex body C. And to form the packing, we just translate it, or we translate it and scale it to form all the other shapes in the packing. So no rotations are allowed whatsoever. Okay. Here's two examples. These aren't particularly too interesting, but these are homothetic packings, but I've not actually scaled anything either. But you'll notice that, so this is just the disks. I've just translated them. No scaling's happened. And this is something like the L4 unit ball or something like that. And all I've done is I've translated it around.
I have a quick question.
Yeah.
Are your convex bodies strictly convex?
At the moment, no. Later on, that will play a part. Yeah.
Thanks.
So, oh, actually, I've got an example of one that's not strictly convex here. So I've got some square packings here. The one on the left is a homothetic packing of squares. You notice I've just got one square and it's been translated and scaled to form the other two. This one isn't, because it's not even a packing because there's an overlap, but this square has also been rotated, which I'm not allowing at the moment. Okay. Right. This is possibly a bit elementary, but what I'm calling homothetic packings, I'm calling them C packings for short, where C is going to be some convex body. Every C packing is going to be uniquely defined by, determined by two things. So one is this map P. It's kind of like the realization map or the placement map, whatever you want to call it. And this takes your convex body and translates it. It says, where am I going to translate it? You can also think of it as like, where is the center of my convex body? And then the second map is going to be my radii map. And this just tells me how much I'm scaling it while I'm moving it. I'm not going to do any degenerate packings. So the radii will always have to be positive. So I'm not just going to scale something down to a point. But there is work on this. Oded Schramm did some stuff with this with square packings. But I'm not going to be doing that. Okay, the contact graph is just obviously when you have your packing, whenever two things touch, you add an edge. Okay. Right. Because of this, any C packing can be just identified by this triple. So you've got the contact graph G, placement map P, radii map R. That gives you three things. And occasionally I'm just going to say the C packing P is just equal to this triple. So if you see this notation, that's all it means. I'm just saying I have a packing, contact graph, placement, radii. All right. Here's a quick example. It's a bit of a weird one, but this is another square packing. I put all the edges in red, which are kind of like the standard edges. But you'll notice I've also got these two weird diagonal edges, which I've colored in blue. Because this square and this square are touching. So there is an edge between them in the contact graph. Now, this could be a problem when we're doing stuff with convex bodies. But when we're dealing with centrally symmetric ones, fortunately, there's a nice result from Danzer and Grunbaum, which basically says that squares are the only ones where this is going to happen. So every other one, if we think about how the contact graph is embedded into the plane from the packing, it will always be planar. So we don't have to worry too much about that sort of thing. Okay. Right. So as Phil mentioned, going to have to need some extra tools for the moment. So One of them is strict convexity. So this just means that your boundary doesn't contain any line intervals. And because we're just doing stuff in 2D, you can just think about like, there's going to be no flat sides to any of your shapes that you're looking at, okay? And smooth means we're not going to have any corners. It means the boundary, if you pick a point on the boundary, you've got at most one tangent hyperplane, all right? So smooth is a bit of a weird term here because it's not smooth as in infinitely differentiable. It's a convex geometry term. It is more close to differentiable boundary than the term smooth, but this is the terminology. Right. So Oded Schramm came up with this result. He actually proved something way more general than this. I'm just giving it as convex body packings. But he proved in his thesis, I think it was, that if you C is just any smooth convex body in the plane, and if you give me a planar graph, then I can just make a C packing with that contact graph. So this is the convex body equivalent of the Kobe, Andreev, and Thurston results, the cat theorem. Okay. The smoothness is actually required, which I'll get into in a second, but it's worth noting that central symmetry is actually not required for Schramm's result at all. He proves things in a very different way to what I'm going to be doing, but he doesn't require central symmetry. The result isn't actually true if we drop smoothness, interestingly. It's not a massive surprise in some ways. If you think about square packings, if you put 4 squares together, or if you put 3 squares together to form a triangle, and then you want to put more squares in the middle, then to do so, you would need to have like degenerate square packings. So anything with like any sort of planar graph with a separating triangle, something's going to go wrong if we try to do this. But Schramm's result says these, as long as you assume smooth, nothing goes particularly too bad. He also proved, I don't know if it was in the thesis, but he did it a year later at the very least, that if we add some conditions, so if you say that C is also strictly convex, and we say that G is a triangulation of the sphere, so it's a maximally planar graph, then the C packing we get is actually going to be, it will just be unique. It'll be the unique C packing that does this. When I say unique, I do mean unique up to the choice of your 3 outer convex bodies, because you always have to have 3 on the outside, and up to the choice of wherever you put them, you can put them wherever, and there'll always be some corresponding C packing with this contact graph, which is kind of like the cat theorem, but we're avoiding using words like Mobius transform and stuff like this, because it doesn't really mean anything in this sort of language. Another thing that this work that I'm talking about is quite inspired by is some of this stuff about disk packings with generic radii. So when I mean generic radii, I'm just meaning a set of finite real numbers, but they're algebraically independent of the rational numbers. And I'm also going to be mentioning something called these 2K sparse graphs. And these are going to be graphs where every subgraph has this bound on the edges. So the K here is going to actually, so the first number, the 2, in the 2K sparse, is kind of to do with the amount of dimensions of how a given convex body can translate. So the degrees of freedom of a convex body in some sense. So if you were to take a circle, then its degrees of freedom are going to be just the translations. If you get a circle packing, when you pack everything together, you're going to have 3 degrees of freedom on the circle packing, because you've got 2 degrees of freedom for translating it and another degree of freedom for rotating it. Now with this homothetic packing, we're going to have 2 degrees of freedom of our convex body because we're not allowing it to rotate. But then we're only going to have 2 degrees of freedom of the whole packing because we can't rotate the whole packing either because rotations aren't allowed. So this is kind of why we need to look at these sort of graphs. They crop up a lot in rigidity theory, for multiple reasons, and so this is the intuition why these sort of things are coming into play. I'm not going to be talking too much about it, but there's a lot of rigidity theory kind of underneath the surface on this sort of stuff. Right. With disk packings, we got this quite nice result. So if D is going to be the unit disk in the plane, and we have P is going to be our disk packing, assuming that R, the radii, is a generic set, then the contact graph will have to be a 2-3 sparse planar graph. Okay? So it's basically saying if I give you a disk packing and you know that the radii are random, just effectively randomly chosen, then you know that almost certainly it's going to have a 2-3 sparse planar graph. So this isn't to do with, well, so firstly, interestingly, if you have something where the radii aren't random, then the contact graph can be any planar graph whatsoever. This comes from cat theorem. And that gives you quite a high bound on the number of edges, but which is kind of like a 3-6 sparse bound. But as soon as we assume this randomness, it drops right down to 2-3. So it's quite a significant drop. And this is a theorem of Bob, Shlomo, and Lewis from a couple of years ago. I'm just going to, so they actually just to first say, they actually prove something a lot stronger. I'm just giving the result that's required for what I'm talking about. They also talked about sticky rigidity and stuff like this. So they prove some extra stuff, but this is just part of the result. So in layman's terms, if I give you n circular coins, and I've just chosen the radii to be completely random, and then I give them to you, and you just put them on a table, and you slide them around however you want, and stick them together, but we're not allowing you to kind of overlap any two coins. Well, if you do this, the outcome is going to be that the amount of the coins are going to have at most 2n-3 contacts between them. So this is kind of something you get immediately from the result. It's kind of a practical application of it in some sense. So this is the disk packing version. But we want to generalize this to this idea of convex bodies. All right. So we're now going to centrally symmetric convex bodies. We're adding the restrictions that they're strictly convex and smooth. So no straight edges, no corners. And they have this 180-degree symmetry. You notice I've gone for almost all. Basically, the idea of generic here is because circles are defined by a set of algebraic constraints, x squared plus y squared equals 1. Well, most convex bodies are not described by a set of algebraic constraints. So using generic as this algebraically independent thing is going to be completely useless. It's not going to help us. So instead, we go for the next best thing, which is this kind of measure theoretic sense. So an almost all just means that the set where it doesn't work is going to have measure 0, Lebesgue measure 0. So for almost all choices of radii, so for a random set of radii, if you randomly pick radii, this is going to be true. Any C packing with radii R will have a planar 2-2 sparse contact graph. Okay. Now this still covers the circle case, just because every 2-3 sparse graph is automatically also 2-2 sparse, and you can just see this from the count here. Because if this is if you know that you got a circle, you know this is going to be 3. Well, that's automatically less than if it was -2 instead. So this still covers the circle case. Right. What can I say about this result in kind of layman's terms? What I'm going to say is I tell you that you can describe any centrally symmetric convex body with the proviso that it has no corners and no flat edges. All right. Once you've chosen this, I then choose a load of random positive scalars. I just randomly choose them. I now give you n coins, where each coin is just, so each coin Ci is going to be C, the convex shape that you chose, scaled by Ri. Okay? Now I tell you, put them on the table, and you can slide them around however you want, but the restrictions now is you have to keep the orientation. So once you put them down, they all have to be in the same orientation. You can't start rotating the coins, but you're allowed to slide them around however you want. All right. The outcome from this is now that when you do this, put them all together, you're going to have at most 2n minus 2 contacts. Okay? So this is the generalization of the previous result. Right. What about the converse? So I've just told you that if you have a packing with generic radii, say if we got a disk packing, oh, I've got a question. This means homotheticity. Yes. So all the packings will be homothetic, the homothetic packings. Yeah. So if you have a disk packing and you have generic radii, then you know the contact graph is going to be 2-3 sparse. So the reverse question is, okay, if you give me a 2-3 sparse planar graph, can I give you a disk packing with generic radii with that contact graph? Can you give a quick example where the bound is met? Yes, okay, I can. So on the previous one, what you can have is you can have 3 shapes in a triangle. So 3 convex bodies, they're not going to be disks, importantly. Okay? What I'm going to then do is I'm going to rotate these 3 around. Now, rotating is not rotating as in I'm rotating the whole thing, so they all have to stay in orientation. So it's going to be this weird sort of motion going around. Now, what's going to happen is if I've chosen the 3 outside ones generically, their width and stuff should start, well, the radii won't change, but the distance inside that they bound, the largest possible disk I could fit in there, convex body, sorry, that I can fit in there, that will change as these things rotate around. Okay? Which means, unlike with a circle, if you have 3 circles and they rotate round, it doesn't matter if, however generically I chose a radii, as they rotate round, the biggest disk I can fit in between the 3 of them is always the same. With convex bodies, that's not true. And if you do this, then what's going to happen is that could change and then you could fit something in. Now, what I'm actually going to prove later on is that this bound can usually be met. If you give me a random shape, I can usually meet this bound. So that's what I'm going to prove, which I guess is not as satisfying as giving you a direct example, but is, I guess, the next best thing. Does that answer your question? Hopefully.
Yes.
Right, brilliant. Okay, so yeah, so this is what I'm talking about here, the converse. So with the generic packing, we want to say, yeah, if you got the disk packing, can you give me a, if you got the graph, can you give me a generic radii disk packing? And you can say it's true for very basic graphs. So partial 2 trees are these things where, I won't go into it too much, but it's a 2 tree is where you start with a triangle, add a vertex join to 2 edges that are already connected by an edge, and just carry on doing that. And then a partial 2 tree is any subgraph of that. And if you have something like this, then it's very easy to prove that you can do this sort of thing. And these are also equivalent to the 2 flattable graphs, but I won't go into that. But yeah, so this conjecture is hopefully true, but at the moment it's still open. Because it was quite a hard conjecture, I decided to answer an easier question, which is to show, is this true usually? So this is what this result talks about. I'm going to break down what it means because there's a lot of weird terms in it. But yeah, so I'm going to say there exists a co-Omega subset G of the centrally symmetric convex bodies in the plane. So the centrally symmetric convex bodies in the plane, they have a natural topology, which is generated by the Hausdorff distance. And it makes them locally compact. In fact, they're a Baire space. And a Baire space is a space where every co-Omega subset is going to be also dense. So what's a co-Omega subset? A co-Omega subset is just going to be the countable intersection of open dense sets. And this is all to do with Baire category theory and stuff like this. Now, the reason why you want to result with co-Omega subsets and stuff like this is basically, topologically speaking, your best possible bet when it comes to talking about an almost all result. We don't really have a measure on the set of centrally symmetric convex bodies, so your next best thing is to do this topological variant, talking about co-meager and meager. You might have also heard of residual and co-residual, and they're the same thing. Okay, so this is why we're using co-meager. So what this says is that there's a co-meager subset of the centrally symmetric convex bodies. I don't have to assume strictly convex or smooth or anything. There's a nice subset of these bodies where we have this equivalence. And the equivalent is saying that if I have a graph that's a 2-2 sparse planar graph, then this is going to be equivalent to the fact that there's a set of radii with non-negative measure, where for every radii in this set, there's going to exist some placement so that we have a C packing with G as the contact graph. So I'm going to explain this in layman's terms, but that's what the theorem says. So this set, if you choose something in this set, so we just pick any convex body out of this co-meager set, then we're going to do the following. I'm going to say to you, describe any 2-2 sparse planar graph you want, whatever your favorite one is. I'm now just going to randomly choose some positive scalars, whatever I want. I'm now going to give you the n coins like before, where Ci has been scaled by Ri. And what's going to happen is, if you move them around, or sorry, what's going to happen is, with respect to our choice of radii that I randomly chosen, there's going to be a non-negative probability that you can put them down on the table and rearrange them and stick them together so that the contact graph is the graph that you described in the first place. Okay? So is there any questions about this? Because I know this is a bit of a headache.
What do you mean non-negative probability? Probability greater than or equal to 0?
Apologies. That should be... I was looking for typos beforehand, and you always miss them. This should be positive measure.
Thank you.
I apologize.
Otherwise, I could...
This is trivially true with non-negative. That's correct. This is positive measure. Very sorry. And there should be positive probability. I was just checking beforehand, and I still missed this. Anyway.
You're going to have some pictures for us soon?
What, sorry?
Are you going to have some pictures for us?
No, this is, I mean, I only had half an hour, so this is basically the end of the talk, really. I had pictures earlier on. That was your picture quota. But yeah, so this is basically saying that this conjecture, while we don't know if this is true or not, it is true for most convex bodies. If you give me a random shape, it is true. Oh, and do you have a lower bound for the probability? No, there is no bound on the probability. We just know it's positive. We know that we can do it. Okay. This is kind of an interesting question. You would have to do it on a graph by graph basis, I think. So for something like, if I said K4 minus an edge, and I gave you 4 shapes, then I think it is, yeah, it's 100% probability, because you can make 3 into a triangle, put 1 outside, and just connect it to the other 2. But it's not 100% probability if I asked you to make K4. That's actually kind of could be quite difficult.
So is there a moral reason that you're able to do this when they're not circles, and you're not able to do it when they are circles?
So kind of the reason is you can avoid bad examples. So with the circle, it's kind of, you're looking at one shape, but when you're looking at all the centrally symmetric convex bodies, if you have a bad shape, you can always just kind of perturb slightly and get to a better shape. And that's kind of the idea. This is all based on, so a lot of the rigidity theory is hidden, but what I'm effectively doing is looking for packings where the corresponding framework is going to be independent in the norm spaces in. And this independence makes some map an open map, and then this gives you all the nice stuff that comes with it effectively. And this is basically the idea. So there's a lot of rigidity theory under the water that I'm kind of covering up, but it is there. And yeah, with these things, you're basically then saying I'm perturbing what sort of norm I'm looking at to a nicer norm. And you can always just perturb slightly to something that's a bit better. That's the moral of this, basically. So there's a few open questions on this. So my first result required strict convexity and smoothness. Are these required? Well, the result works for strict convexity and smoothness. That is in some sense needed for some of the technical lemmas, but it doesn't necessarily mean it's needed for the result, which I won't go into, but there is some technical lemmas that require you build a manifold essentially, and you want this manifold to be differentiable. And to have this, you need strict convexity and smoothness to do this. But that's not the only way you could go about proving the result. And I do have some preliminary results. It's not published at the moment, but you can basically, with homothetic square packings, you can get the same result. And you can get some kind of nicer variants of it as well. But the proof is very just elementary combinatorial. It's not anything too crazy. Can we drop the requirement of central symmetry and allow multiple convex bodies in any of the results? Now, from preliminary research I'm doing at the moment, the answer seems to be yes, but you have to increase the restrictions on what sort of things you're looking at. So you would kind of require that your convex bodies have positive curvature. And the reason is you look at something called the support function of the convex body, and you want this to be very well behaved. And the best way to do that is to have positive curvature. Now, this doesn't mean we have a large class, but it does mean we can start looking at elliptic packings and stuff like this. So packings of ellipses. And the ellipses will be allowed to have been rotated beforehand, but then the only problem is they have to stay in the same orientation. So there's some hopeful work to be used to improve this. And this is my last point here. So can similar methods be applied to packings where homotheticity is not required? So, which is quite hard to say. So we allow the convex bodies to now rotate. So when I've given you the coins, and you put them on the table, you're now allowed to rotate them. That will be the true end game of this sort of result. Because this will give us a lot of a very good idea on how matter behaves, and with randomly sized things and stuff like this. And obviously, what can we say about packings in higher dimensions? A lot of these tools are kind of based on ideas of Bob, Lewis, and Shlomo's result that I mentioned earlier. And this result requires some 2D style tools. But it's an interesting question to see, can we change the tools? Can we use different tools to take this to higher dimensions? It might be easier in some sense to get a similar result to this theorem here in 3D because of this idea that if we have a bad shape, we can always just perturb to something better. So there's possibly some hope on proving something like this. Okay, and here's my list of references. And I've got a few minutes, I guess, for any questions.
Does anybody have questions?
Yes. What is your feeling on that question about removing homothetic?
So I gave it a try, and it seems hard but doable, I think, maybe. It was, so my first try was with ellipses, and what I found was if I give you a set of ellipses and the radii is allowed to be random, but the angles are predeterminedly fixed, then that's fine. That can actually be done. And the tools are not too different to what I use, but you have to use these support functionals, like I said. It's kind of the manifold you're looking at starts to break down when you allow rotations into it. It kind of starts messing things up. Also, the numbers are not going to be anywhere close to the same. So the contact graphs will, I think, be a lot higher. The counts will be a lot higher because essentially you've got 3 degrees of freedom on everything. It can translate and it can rotate. So it should have a 3 something count, but
I thought the count was different for that because given the amount of freedom, the rotations and everything, sometimes you can have a lot fewer. Is that right?
I mean, you can always have a lot fewer. I need to think.
So in a sense, you don't have first order rigidity, but you have kind of higher order rigidity when it's jammed.
Ah, okay. But I would assume that we were trying to avoid jamming by doing these kind of random radii results, but maybe I'm wrong on this. So my initial thought was if you have three ellipses on the outside and 1 in the middle,
right?
That's touching all 3. If you rotate the 3 on the outside, the 1 in the middle can also rotate with them, basically. So you've got that's not rigid. So then it kind of makes you think that there's possibly more is required.
But if you have something like an ellipse inside a triangle, first I know you're not doing a triangle, but there are only 3 contacts and it has a kind of infinitesimal motion when it's jammed.
Oh, okay. I don't know then. I'll defer to you on this because my initial things didn't work. But I think you can have anyway. But yeah, I think that you'll have 3 degrees of freedom, but maybe I'm wrong.
So you looked at ellipses in that case of the non-homothetic, you said?
So I didn't bother looking at ellipses for the homothetic stuff just because an ellipse packing in this case will just be a stretch circle packing.
But I mean for the non-homothetic, you looked at ellipses.
Yeah, I did, yeah.
You happen to look at Rayleigh triangles?
No, these are the triangles with constant width. No, I didn't. That's actually an
I
interesting.
think that might be interesting.
Yeah, that could be quite interesting, actually. I hadn't thought about them. No, I didn't. But I would actually like to look into it. I think that's a good idea. Is there much known on these sort of packings?
Who are you asking?
Anyone, I guess.
So Elias, do you have a lower bound on the probability? There's some other questions here in the chats we didn't talk about.
So the lower bound on the probability, no. It's just we know it's a positive probability and that's it. I think you would have to do it on a kind of a case-by-case basis with different shapes. So that makes it quite difficult. I think I could construct it in some way. Yeah, I think maybe not actually. I would have to think about it, but I think there's issues to be said. I don't think it would be very easy to do at all to give any sort of lower bounds on these probabilities. I just know it's not 0, I guess, is the moral.
Do you have a quick example where the bound is met? Did you answer that already?
Yeah, that was the, well, I didn't answer the example, but I answered it with the result.
Okay.
If you draw a shape, then it's probably correct, I think, is the moral.